This lesson is going to be about the complementary trigonometric identities. Now for this lesson, I only really need the first quadrant of the unit circle, so let me go ahead and draw that in. So let's start with the definition. Complementary angles are two angles that add up to 90 degrees or pi on 2 radians. So we've shown this in this little picture. If you add alpha and beta together, you'll get 90 degrees or pi on 2 radians, just like we said. Now if I pick some random angle theta on the unit circle, then its complement can be drawn in too. Now since we usually measure angles from the positive x-axis, we shouldn't start over here, so let's move the angle back to the positive x-axis. Now let's pretend for a moment that we called this angle x. Since we know that x and theta add up to give us 90 degrees, then we can solve for what x should be. So as you can see, this blue angle x is just pi on 2 minus theta, so we can write that right away. Now if we just go ahead and show the point of intersection of this first point, we can label it x and y, and we know that's the same thing as cos theta and sin theta. Now if we look carefully at the other point of intersection, you'll notice that there's actually a very close symmetry between these 2 points. If you look really carefully, you'll notice that the x-coordinate of this point is just the same thing as the y-coordinate of this point. Both of them are equal to this letter x. Now because these are both exactly the same, we can immediately see that the y-coordinate of this point is just the same thing as x, so we can write that in. Now we can go ahead and hide these markings to find this missing part of the coordinate as well. Now if we look carefully again, we're going to actually notice that the y-coordinate here is the exact same as the x-coordinate here as well. So we can write that the x-coordinate of this point is exactly the same as the y-coordinate of this point. Now I'd like to remind you that the first half of the coordinate is the same thing as cosine pi on 2 minus theta, and the second half of the coordinate is the same thing as sine pi on 2 minus theta, which we can label now. Since both of these are y's, then we can immediately say that the sine of theta is the exact same thing as cosine pi on 2 minus theta. Also, since both of these are x's, then we can immediately say that the sine of pi on 2 minus theta is the exact same thing as the cosine of theta. Now of course, the presence of these pi on 2's indicates that this is only true in radians. You'd swap these for 90 degrees if you wanted it to be true for degrees as well. Now's probably a good time to bring out a calculator and show you that these actually work. So just picking two angles at random, we know that 40 and 50 add up to 90 degrees. So the question is the cosine of 40 degrees the same thing as the sine of 50 degrees? Well, to do a basic check, let's just type both values into our calculator and see if they're the same. However, you shouldn't forget that your calculator needs to be in degrees since these angles are in degrees. So as you can see, it is true, the cos of 40 degrees and sine 50 degrees are the exact same thing. Now it turns out that you can actually find other points that obey these complementary like identities. So let me just go ahead and get rid of this and show you an example. So it turns out that we can express all three of these values in terms of nothing but 15 degrees. The first step to solving pretty much any problem like this is to draw a unit circle, as you probably would have guessed by now. Now it would be a good idea to express these two angles in terms of degrees as well. So to do this for radians, remember that pi radians is the same thing as 180 degrees. This means that a radian is just 180 on pi degrees. So that means for 7 pi on 12 radians, we can just swap the rad for 180 on pi degrees. If we simplify this, we'll see that this is just 105 degrees. In the same way, we know that rev is 360 degrees. That means we can just swap the rev for 360 degrees in minus 5 on 24 rev. Now if you plug this into the calculator, you'll find that it's just minus 75. So we'll go ahead and mark these other 3 points on the unit circle directly. Now we notice that all three of these angles are 15 degrees from the y-axis, which we can draw in. If we labeled our initial point CS to abbreviate cosine and sine, since we're looking for the sine of 75 degrees, then we're looking for its y-coordinate. We can see that the x-coordinate of our original point is just the same thing as the y-coordinate of our new point. That means the sine of 75 degrees is just the same as the cosine of 15 degrees. This time we're looking for the cosine of 7 pi on 12 radians, and you can see very clearly that it's actually a negative number. However, its height is the same thing as sine of 15 degrees, so it's just the negative of sine 15 degrees. This shows that you have to pay particular attention to when things are negative or positive. Now for this last angle, we just want its gradient, so we should look at the rise over run of this point. As you can see, for the tan of negative 75 degrees, we're rising by negative c and we're running by s. Now we see something a little bit interesting here. We know that tan is usually sine over cosine, but this time we have cosine over sine, so we have the reciprocal of tan 15. Now I wouldn't suggest you try to remember any of these things because there's just way too many of them to remember. I always suggest drawing out the unit circle and trying to figure out how things are related. So we'll just move away the book and the calculator for now. So as we demonstrated, these complementary identities are really useful, and they come straight from the unit circle. And with that, we've completed our discussion on the complementary identities.